Okay, in this video, we're going to solve this practice problem on weak acid, strong base titration, which is where we left off at the end of the previous video covering weak acid, strong base titrations. Also in this video today, we'll discuss two other concepts of indicators and polyprotic acids. But let's begin going over this practice problem where you can feel free to pause the video here and try yourself first. This practice problem demonstrates the four different types of problems you could be expected to solve in a weak, strong titration. That corresponds to the four different regions of a titration before the titration even begins, part A. After the titration begins, but before the equivalence point, part B, part C at the equivalence point, and part D after the equivalence point. So let's go through one by one and solve each of these four different types of problems for this one sort of setup where we're having 40 mils of 0.1 molar weak acid down in some beaker. And we're titrating it with this strong base NaOH, which we'll just represent as OH minus. So let's think about part A here, where we haven't even started the titration yet. So there's been 0 milliliters of sodium hydroxide added. All we're doing is determining the pH of a weak acid down here. And if it was a strong acid to get pH, we would just do negative log of that acid concentration. But it's not a strong acid, it's a weak acid. And for a weak acid, we have to worry about its equilibrium and its Ka. So let's think about what this acid is. Propanoic acid, C2H5COOH. It has its own equilibrium. It's just floating around, right? It's going to break apart into H plus and C2H5COO minus. I can think about an ice chart here and an equilibrium, starting with nothing on the right and starting with my initial weak acid concentration on the left, 0.1 molar propanoic acid. The right side will go up by plus X. The left side will go down minus X. And so my equilibrium constant, my acid dissociation constant as it were, is going to be equal to this products over reactants, x squared over 0.1 minus x. And here you can neglect x, as we've talked about in the past, neglect it in the denominator down here. Multiply 0.1 by both sides, take the square root. That'll allow you to solve for x and get 0.00114. This is less than 5% of the thing I neglected it with respect to. 0.1 is less than 5% of 0.1, so it was safe to neglect it. And now this X represents my H plus concentration, so now I can just take negative log of that concentration, 0.00114 molar, to get my pH here for part A of 2.94. Right, so that's a problem we've done previously in previous videos where it's just the pH of a weak acid. That's all it is before the titration starts. Now, part B is after I've added 10 milliliters of 0.1 molar NaOH. 10 mils, 0.1 molar NaOH, or just OH minus. And we're adding that to 40 mils of 0.1 molar propanoic acid. And so now I go through the various steps of a titration problem, calculate moles of acid. Okay, well, that's going to be 10 mils, so 0.01 liters times 0.1 molar equals 0.001 moles of base. Calculate the moles of acid, 0.04 liters times 0.1 molar gives me 0.004 moles of acid. And now I can worry about the reaction that's happening here, this propanoic acid now getting OH added to it. The titration has begun. Acids and bases are going to neutralize each other to make water, and the conjugate base of this weak acid I started with. So C2H5COO minus. And I can now do an ice chart on this guy. Using the moles of acid and moles of added OH minus, starting with no conjugate base. I'm going to use up all of the OH minus because that's the lesser of the two numbers here on the left. So that's going to be what's completely neutralized and go to 0. My acid will go down that same amount because it's what's neutralizing the base. So I'll wind up with 0.003 moles of the acid. And the right side goes up by that same amount of moles because I've created this conjugate base in that process of neutralization. So now I'm before the equivalence point because I haven't added enough OH minus to completely neutralize my acid. And so I know I can use Henderson-Hasselbalch because I'm before the equivalence point, where the pH is the pKa, so negative log of the Ka. Henderson-Hasselbalch is pH equals pKa plus log of base over acid, and I'm free to just use the moles here. You can convert it to concentration by dividing both moles by the same liters here, which is 0.05 liters, 40 plus 10 milliliters. Okay, but again, I am free just to use the moles here instead because the liters would cancel out. And so this is my Henderson-Hasselbalch. I enter all this in and I get a pH of 4.41. Okay, so that is part B. And compared to part A, the pH went up from 2.94 to 4.41, which makes sense because I've added some OH minus. Now, let's look at part C. Part C, it just says I'm at the equivalence point. Okay, so I still have my 40 mils of 0.1 molar propanoic acid. So that is still going to be thinking about 0.004 moles of propanoic acid. If I'm at the equivalence point, then that means I have the same amount of base. Okay, and I know my base is 0.1 molar NaOH. That's given in the problem, 0.1 molar NaOH. So I must be adding 40 mils of 0.1 molar in order to get 0.004 moles of base, which is what's required at the equivalence point, where we know moles of acid equal moles of base. Okay, so I'm working backwards here to figure out, okay, at the equivalence point, actually how much base have I added? It's not always going to be the same milliliters, but it is here because the concentration of acid and base is the same. Okay, but that's not always going to be the case. So at equivalence, start with the fact that moles of base will equal moles of acid. That is a given at the equivalence point. Figuring out what the moles then of the base is, and convert it back to liters by using the moles per liters here. So moles divided by molarity will give you liters, and you can convert then to milliliters. Okay, so all that to say, I'm still having the same reaction here. It's just now I have the exact amount of base to completely neutralize the amount of acid I'm starting with. So 0.004 moles of acid, 0.004 moles of base. Both of those are going to completely get neutralized and go to 0. And my right side is going to go up by 0.004 as a result of those two things neutralizing each other. Now, we talked about in the previous video how the next step after you figure out at equivalence point how many moles of the conjugate you've created here, it's time to turn this into a concentration. So you need to take this moles of base and divide it by the total liters, right? Which is 40 plus 40. So it is important to figure out how many milliliters of base you added, because here's the point where we have to use the total volume of 0.08 liters. So now I have this concentration of conjugate base that I've created. Okay, 0.05 molar. And now the step is to think of this as a new reaction. Okay, you've added the base, it's completely neutralized the acid, and you've made this conjugate base. And now the conjugate base is just floating around in water. And what is that base going to do? Well, it's going to steal a hydrogen from water to make its conjugate acid and leave behind an OH minus. Okay, so these equivalence point weak, strong titration problems will always require, at least the way I am teaching it, a second ice chart where the reaction is just the reverse of the first ice chart. So this reaction right here is the reverse of this first reaction we used, right? Because it's just neutralizing the acid and base, setting up the conjugate base, which is going to then reshift to make its reactants again. Okay, so now this second ice chart is thinking about this second stage of the reaction where now I just have this 0.05 molar conjugate base floating around. What is it going to do? Well, it's going to start to decrease by some amount X. The products are going to go up by that some amount X. And now I can have an equilibrium of products over reactants where I'm using the equilibrium dissociation constant here of the base Kb, even though I was given a Ka. This second ice chart is based on a conjugate base of that acid, so I need the Kb. And the Kb here I can solve for, because I know the Kb is Kw over Ka, where here Ka is given in the problem as 1.3 times 10 to the negative 5. So I'm taking that Ka, turning it into a Kb. Here I get 7.69 times 10 to the negative 10 as my Kb. And now I can solve for x by neglecting x. Solving for x, 6.20 times 10 to the negative 6. That is less than 5% of 0.05, so that's a safe assumption. And now I have my amount x. What does x represent here? In this second ice chart, the amount of OH minus. So negative log of this concentration of OH minus is going to be my POH. Negative log of 6.2 times 10 to the negative 6 is 5.21. That's my POH, but I'm asked in the problem for the pH, so I do 14 minus that to get the pH of 8.79. Okay, and that makes sense because for a weak acid that you're titrating with a strong base, at the equivalence point, you will still have this conjugate base left over floating around in water after you've completely neutralized in the first step. And so your equivalence point solution will be basic. You should have a pH greater than 7 here, which is what we find. So at equivalence point for weak acid, strong base, your pH should be greater than 7. Strong acid, strong base, it's exactly 7 because there is no base or acid floating around. Here there is. Okay, so that's part C of this problem. Okay, part D of this problem, after 60 mils of sodium hydroxide have been added, well, moles acid, moles base. Moles of acid is still thinking about this as 0.004 moles of my acid. Moles base, well, now I'm considering the scenario where I have 60 mils or 0.060 liters times 0.1 molar. So 0.006 moles of base. And I'm still going to have this same sort of reaction that I'm thinking about. The weak acid is getting strong base added to it. It's going to make water plus its conjugate. Now, in this scenario where I'm asked the equivalence point, that means I've added too much OH minus, and so my moles of acid will get completely used up. So entering the moles here into my first row looks like this. My acid is going to be what's completely neutralized because there's more base than acid, so the acid gets completely neutralized and leaves behind some of the strong base. I've added too much strong base, so there's still, after these things neutralize, going to be some strong base left. There's also going to be some conjugate base created here. But we won't end up worrying about that. And the reason is because if we have this solution now where there's strong base OH minus just floating around and weak base floating around, the pH is really only going to be dictated by the strong base. The weak base is going to affect the pH negligibly compared to all the strong base. So really, now all we have to worry about is the concentration of excess base here. And so we'll take the moles from base of strong base from our ice chart, divide by the total liters here. Well, wait, what is the total liters? Well, 40 mils of acid to start with. I've added 60 mils, so that's 100 mils total, or 0.1 liters. And so my concentration here of OH is 0.02 molar. And so now I can take negative log of that to get my POH of 1.7, and my pH then will be 14 minus that, or 12.3. And that is a very reasonable pH after the equivalence point. When you've added too much strong base, you're going to have a solution that is very basic, a bunch of strong base floating around in water. Okay, so that does it for this practice problem where we talked about the 4 different types of calculations you could do based on being in 4 different parts of the titration, before the equivalence point, at the equivalence point, and after the equivalence point. A couple more concepts I want to talk about. You can be asked to do all of the same types of problems, but for a weak base, like NH3, a prototypical weak base, that you're adding strong acid to, like HCl. Okay, so before we had a weak base up here in the burette that we were dropping into we had a strong base up here in the burette that we were dropping into a weak acid. Now we have a strong acid that we're dropping into a weak base. Okay, you're still doing all the same types of things. You're just thinking about this as the reaction of the weak base with this strong acid, and you're making its conjugate acid, right? So the weak base here, the strong acid here, and now you have a conjugate acid, right? Some people write this instead as NH3 plus H3O plus instead of H plus, because sometimes they like keeping track of the actual water, even though it's going to drop out of your ice chart, right? But both of these reactions are the same, just depending if you're writing H plus or H3O plus. But this is the type of reaction you will have. You will still have to decide, where are you here? If it's before the titration starts, well, then you're doing an ice chart and using a, not Ka, but a Kb, because you have a weak base. And if you're before the equivalence point, you're still going to wind up with a base and acid, conjugate base, conjugate acid pair that you can plug into Henderson-Hasselbalch. Or at equivalence, you would wind up, at equivalence, you would wind up creating the conjugate acid here that you'll have to turn into a second ice chart and worry about its Ka from the given Kb and calculate the pH, because that's what you'll have in the very end of the second ice chart. Okay, so there's a lot of symmetry here. It's all the same steps. It's just you're starting with a weak base instead of a weak acid. And so you're creating a conjugate acid instead of a conjugate base. And you might have to use Kas versus Kbs. And you might be calculating pH versus pOH. But if you master the practice problem we've done here, you should be able to do similar problems for weak base, strong acid titrations. Now, two more quick concepts to go over. The first is indicators. And an indicator is a weak acid. Okay, so we'll just write HA as our weak acid. And this is something whose equilibrium can shift depending on the pH. And so during a titration where the pH is changing, you will be shifting back and forth between two different forms of a conjugate acid base pair for this weak acid indicator. And the indicator has the property where actually one of its conjugates is going to have a different color. And so for the example of phenolphthalein, when it's acidic, it's clear, and when it's basic, it's pink. So you will add an indicator molecule to a beaker of stuff that's undergoing a titration so that when that pH changes throughout your titration, you have a visual indicator of that pH change. And so indicators are just these weak acid molecules who have a color change that you add into your weak base or weak acid that you're titrating. So you have some visual evidence of when the equivalence point happens, when this big swing in pH happens. And that will tell you you've reached the equivalence point. Okay? Which will tell you moles of acid equal moles of base and tell you something about the unknown concentration of acid or base. And there's a lot of molecules you can choose here for an indicator. That choice can be critical because you want to make sure it's changing colors at the equivalence point. Okay, so you don't want to choose methyl orange where it changes color around a pH of 4. If it's a weak acid strong base where the pH is going to change around 8 or 9, you use something like phenolphthalein instead. The other quick concept I want to go over here is polyprotic acids. We won't do titration problems on polyprotic acids, but I do want to discuss what a polyprotic acid titration reaction would look like, and the notion that there's going to be an equivalence point for each dissociation. So remember, a polyprotic acid is something like H3PO3, okay, where that can donate a proton. And then this conjugate base that's created can actually itself end up looking like an acid and donate a proton. And this HPO3, well, that can donate a proton. And so there are many protons, or polyprotic acids, right? So here there's 3 in this polyprotic acid. And each one of these reactions you can think about as doing a titration on and reaching an equivalence point. And so you can have, our titration curve where instead of just looking like one equivalence point, right, the polyprotic acid would look like this. There's an equivalence point, there's an equivalence point, there's an equivalence point. Okay, here, here, and here. All right, so that's the only concept I want you to be aware of. For polyprotic acids, you would have titration curves that would have sort of 3 steps to them if there's 3 protons, or 2 steps if there was only 2 protons, where our other monoatomic acids only have a single equivalence point. Okay, so that'll do it for this video where we went over this practice problem of weak acid strong base titrations, and then talked about indicators and polyprotic acids. Up next, we'll dig into solubility and how the common ion effect will affect solubility. But that's up next time. That'll do it for this lecture. See you next time.